Chapter 15, number 1, a cell is prepared by dipping a copper wire into a saturated silver chloride electrode into a 0.10 molar copper sulfate solution, and this is CuSO4, so we know that this is copper 2. The copper wire was attached to the positive terminal, and the reference electrode was attached to the negative terminal. So A, first we're going to write the half reaction for the copper electrode. So we're going to start with our copper 2, and we know it's copper 2 because it's in copper sulfate with this chemical formula. Remember, sulfate from general chemistry, sulfate has a charge of -2. So in order to make this compound make sense, copper must be a +2. So we're going to reduce it with 2 electrons, and it will be in an equilibrium with solid copper. B, write the Nernst equation for the copper electrode. So the Nernst equation, this is going to be reduction. Copper attached to positive, so this is our E positive. That is reduction. That is our cathode, and that is going to be 0.339 because that is the reduction potential of this reduction half reaction, minus our 0.05916 constant divided by the number of electrons transferred. We have 2 here, times the log log of the Q. So we have products. 1 is the activity of a solid. So 1 over the concentration of our copper 2. So the concentration of our copper 2 is given to us right here, and that is 0.10. And when we punch all of this into the calculator, you should get an E plus value of 0.309 volts. So that is the potential of our cathode. So C, calculate the cell voltage. Well, you need to know the E of the anode. So the E of the anode is going to be the silver chloride standard cell potential, so 0.197. So the E of the cell is still going to be the E of the cathode minus the E of the anode. It's just the E of the anode is our standard silver chloride cell. So 0.309 minus 0.197. You should get an E of the cell then of 0.112 volts. Number 2, platinum and saturated calomel electrodes are dipped into a solution containing this amount of bromine and this amount of bromide. Platinum is attached to the positive terminal. So the platinum attached to the positive terminal, that tells us that it is attached to the cathode. And our calomel electrode is going to be the anode. So we're going to write the reaction that takes place at platinum and find the half cell potential. But I'm going to do the anode first because that's just what I'm more comfortable with. So the E of the anode, the saturated calomel electrode, if you don't remember it, is going to be found in the class. And I thought I had that open, so here it is, the standard reduction potentials table, and I'm looking for mercury. So coming down here to mercury, you should be able to pick out which one of these is the standard calomel electrode. And conveniently enough, Harris has pointed out for you that the standard calomel electrode is 0.241. And see, there's a little arrow even pointing it out to you. So I'm going to write that one down first. That's going to be my anode. So the reaction that takes place at the platinum is going to be a reduction reaction, and it's going to be bromine in equilibrium with 2 Br minus. So I have this, yes, reduction is gain. I'm gaining 2 electrons. So this is the reaction that takes place at the platinum electrode. So I'm going to go back to my standard electron potential, standard reduction potentials, and I'm looking for bromine. I want to find out what that standard potential is. So here we are, it's 1.098. So when I go to write the Nernst for that, the E plus is going to be 1.098 minus 0.05916. That is my constant, divided by 2, because I have 2 electrons being transferred, times the log log of the Q value. Well, in this case, these are both aqueous So they are both part of my Q value. So I need the concentration of the bromide squared because it's my product and there's a 2 in front of it. There's a 2 for the coefficient, divided by the concentration of my diatomic bromine aqueous. Now these concentrations are given to you and they're given to you right here in the problem. So I'm just going to replace 2, 3, 4. And bromine is also right here. Punch that all into your calculator and you should get an E of the cathode of 1.057 volts. So now to find the E of the cell, I need the E of the cathode, the positive, minus E of the anode, the negative. So I'm going to take 1.057 volts and subtract 0.241 volts because that is my anode. It's the standard calomel electrode. And you should get 0.816 volts for number 2. 3, 4, and 5 are basically permutations of the same question. So I'm going to go over number 3. So if we have a 50 milliliter solution of 0.100 molar sodium thiocyanate, but it's the thiocyanate that's important, was titrated with 0.200 molar silver nitrate in a cell in 15.1. Well, let's find 15.1 so we can see it. Here's 15.1. So you can see the silver is connected to the positive side of the potentiometer. And here we have a saturated calomel electrode on the negative side. So that is our anode, and the silver is going to be our cathode. So I'm going to write that over here. SCE is our anode, and the potential for that is 0.241 volts. So it is this silver and plus 1 electron reacting to form solid silver, and that has a standard reduction potential of 0.799. So we're going to titrate. We're going to titrate this thiocyanate with silver, but we're going to watch it with our potentiometer. So when the volume of the silver, that's what this AG is for, it's for the volume of silver. We're going to calculate the E when we have added 0.1 milliliters, when we have added 10 milliliters, 25 milliliters, and 30 milliliters. So like with any titration, the first thing we need to find is what is the equivalence volume so that we know how to work with our numbers. So I'm going to start with my 50 milliliters of thiocyanate, and that has a concentration 0.100 moles per liter of SCN. And then we have our balanced, we don't have a balanced chemical equation yet. We need to write a balanced chemical equation. So we are going to be reacting silver with thiocyanate, and we were going to form AgSCN, and that is solid. So this is our balanced chemical equation. For every 1 mole of SCN, we need 1 mole of Ag+. Well, the silver nitrate solution that we have is 0.200 moles per liter. So what we find is the equivalence volume is 0.0250 liters or 25.0 milliliters. So this is our equivalence volume. So we are before the equivalence volume when we're working with 0.1 milliliters of silver added. And that's where we're going to start. Now, initially, our SCN, how much SCN do we have to start with? Well, I take my 0.0500 liters, and I'm going to multiply it by the concentration, 0.100 moles per liter. And I get that we start with 5.00 times 10 to the negative 3 moles of SCN. Now, I'm adding to that some silver. And when I add that silver, because we wrote our chemical equation up here, when I add that silver, I end up making this solid. So I have added 0.1 milliliters of a solution that has a concentration of 0.200 moles of silver per 1,000 milliliters. And I get that we have 2 times 10 to the negative 5 moles of silver that were added. Now, because we are working this titration, just like with acids and bases, when we work this titration, we are removing something from our solution. And we're making a solid, so it's not coming back into our solution. So what I need to do with these numbers then is I start with my moles of SCN, and as I add the silver, I'm actually taking moles of SCN away. So then I'm left with an excess of 0.00498 moles of SCN. And that's fantastic, but that doesn't tell me a whole lot. I need a concentration. And I need that concentration because what I'm going to do is I'm going to relate the concentrations to the KSP value for this compound. And I'm going to write this the other way. So the KSP of this compound is 1.1 times 10 to the negative 12. And it's going to be equal to the concentration of the silver ion times the concentration of the thiocyanate ion. I have moles, I need concentration. In order to get concentration, I then need to divide this by the total volume. And at this point, the total volume is 50.1 milliliters or 0.0501 liters. So now I have an equation that has one variable I don't know, because the concentration of my thiocyanate is 0.0994 molar. So when I do that division, I find that the concentration of the silver after I have added 0.1 milliliters, because we know that some of this comes back, we have a little bit of an equilibrium. The concentration of my silver is then 1.1 times 10 to the negative 11 capital M molar. So now how do we use that to find the E? Well, remember we said that the saturated calomel electrode is going to be our anode. So what we're figuring out is what is the E of our cathode. We start with the standard reduction potential, 799 volts. We're going to subtract the ratio of our constant, 0.05916, divided by the number of electrons, which is 1. And I know that it is 1 electron because that's what I wrote right here. So that's where that number comes from. Then I'm going to multiply this times the log of my Q value. Now my Q value, this is the reduction, and I know it's the reduction because the silver was attached to the positive side of the potentiometer. That's the cathodic side. That's where the cathode is. So this is the way it's written. Now this is a solid, so my Q value is going to be 1 over the concentration of my silver. And that's what happens here, 1 over the concentration of the silver that I just found out. So 1.1 times 10 to the negative 11. Now, when you put all of this business into the calculator, you should get the E of the cathode is 0.804, and then I have more digits, 398 and such. So the E of the cell is going to be the E of the cathode minus the E of the anode, the saturated calomel electrode. And I just realized I hit the button wrong in my calculator. So this E of the cathode should be 1, 5, and then I have 0.68. I'm not sure what I did before. I'm going to call it 151. So the E of the cathode, 0.151 volts, minus the E of the anode, 0.241, because that's our saturated calomel electrode. You should get an E of the cell of negative 0.090 volts. Now we do keep our significant digits to the thousandths place. Remember from the very first week, our sig fig rules, when we're subtracting like this, we are bound by the last place value. So it's negative 0.090 volts for the E after 0.1 milliliters of silver have been added to this titration. So now let's do 10 milliliters. So what I'm going to do is basically leave most of what I have done here, and I'm going to replace my 0.1 with 10, and then I'm going to recalculate the parts that need recalculated, like this. So it's the same process with slightly different numbers. So here I have made the changes, and I'm just going to step through it briefly. Our equivalence volume is the same at 25 milliliters, and we actually don't need that at the moment, so I'm just going to get rid of it. We still start with the same amount of thiocyanate, and that's 5 times 10 to the negative third moles. But this time we have 10 milliliters of silver. So we have found that there are 2 times 10 to the negative 3 moles of silver that were added. That means 2 times 10 to the negative 3 moles of thiocyanate have been taken out of solution because they've been made into this solid. So the leftover thiocyanate is equivalent to 0.003 moles, but we need to divide that by the total volume in order to find the new molarity. So we need the concentration of thiocyanate in order to put into our KSP equation to solve for the concentration of silver, because our silver is going to be purely dependent on the amount of silver that comes off of that solid. So then we can set up our Nernstian equation for the cathode. So we start with our 0.779 volts. That is our standard reduction potential for silver. We're going to subtract and then the product of all of this stuff. So we have our constant 0.05916 and divide that by the number of electrons that are being transferred. In this case, it's 1. Then multiply that times the log of the Q value. Now the Q value for our reduction reaction here is still going to be the solid over the concentration of our ion. Because the activity of our solid is 1, then our Q value becomes 1 over the concentration of our silver. Now the concentration of our silver we've found from our KSP equation. So we can find the new cathodic potential of 0.168 volts. We subtract from that the anode potential. This is our standard calomel electrode. And we know it's the anode because in the picture it was hooked up to the negative side of the potentiometer. And we find the E of the cell at this point is now a negative 0.073 volts. Now the process changes a little bit once we get to the equivalence volume, and that's our next setup, is to work this at the equivalence volume. So we start with our 0.005 moles of thiocyanate, and we're adding 0.005 moles of silver. So the concentration of the silver then is going to be purely dependent on how much of the solid it ends up in solution. So these concentrations are purely dependent on the KSP. And we don't know what these concentrations are until we run the KSP equation. So the KSP is 1.1 times 10 to the negative 12, and that's going to be equal to x squared. That's the concentration of the silver times the concentration of the thiocyanate. So the x value here is going to be equal to the concentration of the silver ion, which is what we need, and that's going to be equal to 1.0, and I have more digits, we'll just leave it in your calculator, times 10 to the negative 6 capital M molar. So now just as before, the E of the cathode is going to be 0.799 minus, and then we take our constant divided by 1, because we have 1 electron that's being transferred up here, times the log of the Q value, 1 over the concentration of this silver. That's why we need the concentration of that silver. So like this, and then you should get that the cathodic concentration, not concentration, potential, you should get that potential to be 0.445 volts. So the E of the cell is still going to be the E of the cathode minus the E of the anode. And again, that anode is that saturated calomel electrode. So you should get an E of the cell value of 0.204 volts, and this time it is positive. Now, past the equivalence volume, the concentration of this silver is purely dependent on the excess silver that was added. So we know at this point we have 0.0500 moles of thiocyanate that were added. So at 30 milliliters of silver, how much silver was added? Well, our silver concentration is 0.200 moles per 1,000 milliliters. So 0.03 times 0.2, we get 0.00600 moles of silver added. So we will take away the equivalent amount of moles of thiocyanate because that's being pushed and forced into its solid. So we have 0.00100 moles of silver in excess. We don't need the moles, we need the concentration. So we need to divide this by the total volume. And the total volume at this point is 80 milliliters or 0.08 liters. So the concentration of silver now is going to be 0.00125 capital M molar. That is our concentration of silver. So now we are using the same equation we had before. The E of the cathode is 0.799 minus 0.05916 over 1. We're using a 1 because we have one electron being transferred, times the log log of the Q. The Q is 1 over the concentration of this silver. So you should get a cathodic potential of 0.627 volts. And as before, the E of the cell is the E of the cathode minus the E of the anode. And I added an extra 0 here. So this is 0.0125. I did that here too. So the cathodic voltage is not 0.627, it's 0.686. That makes a little bit of a difference. So now take the 0.241 away, and you should have an E cell of 0.445 volts.